Let's now consider a simple protocol for 1 out of 2 oblivious transfer secure in the noisy storage model. Our protocol will be quite simple and can be implemented with hardware used in QKD, with a small adaptation. Crucially, honest Alice and Bob will need no quantum memory to implement the protocol. A quantum memory would only be convenient for an adversary who is trying to break the protocol. Before delving into the protocol, let's briefly recap what oblivious transfer wants to achieve. We again have our two protagonists, Alice and Bob. Alice has two input strings, S0 and S1, known only to her but not to Bob. Bob has a choice bit, C, known only to him but not to Alice. As an idealized primitive, oblivious transfer takes these inputs and gives Bob the string SC, the string of Alice corresponding to his choice bit. Bob thus gets to choose which of the two strings he wants to get. If the protocol is correct, then Bob indeed receives SC. If one of the two is dishonest, remember that we want the following security conditions to hold. We shall briefly recap informally here. Alice does not learn C. So if Bob is honest, but maybe Alice is trying to cheat, then she cannot learn which of the two strings he gets. That is, she doesn't learn his choice bit C. Second, if Alice is honest, but maybe Bob is cheating, then he cannot learn both S0 and S1. In particular, there is always one input string about which he learns nothing. How will Alice and Bob exchange information? They will connect Alice and Bob, as you may have guessed, using a quantum channel to send qubits. They will also have a classical channel to send classical bits. Of course, if the quantum channel is noise-free, which I will also always assume here, then they could also just use the quantum channel to send classical bits. However, I'll separate the two, since this is the case in any experimental implementations of such protocols, and you can find pointers to this in the lecture notes. So what does our protocol look like? We will again make use of our favorite states, the BB84 states. Indeed, the start of the protocol is quite a lot like BB84 QKD. This is a common feature of protocols in the noisy storage model, and in principle they can be run in parallel and on the same equipment that Alice and Bob use to run QKD. Alice chooses an n bit string, x1 up to xn, and a basis string theta, where, as before, 0 is for the standard and 1 for the Hadamard basis. She sends to Bob the bit encoded in the basis. This time, however, Bob does not measure in a random basis. Instead, he measures in the basis corresponding to his choice bit C. If C is 0, he measures all of the qubits in the standard basis. If C is 1, he measures all of them in the Hadamard basis. So now comes our waiting time delta t. Afterwards, Alice tells Bob which basis she has used. Bob now computes the set of indices where Alice used the basis corresponding to his choice bit C. Remember that there's no noise, so Bob knows all the bits of Alice's string where she measured in the basis C. Alice now chooses two independent extractor seeds, Y0 and Y1, and sends them to Bob. She computes a key, K0, applying the extractor function to all the bits of x where she measured in the standard basis. Similarly, she computes a key k1 by applying the extractor function to all the bits of x where she measured in the Hadamard basis. Here she uses the seed y1. Alice now uses k0 to encrypt S0 using a one-time pad. She XORs every bit of K0 with the corresponding bit of S0 to obtain the message M0. Similarly, she uses K1 to encrypt S1 using a one-time pad, giving message M1. Afterwards, Alice sends Bob the two messages M0 and M1. Bob now computes the key KC, corresponding to his choice bit. He also applies the extractor function to xi and the seed yc. Bob one-time pad decrypts the message MC to get the desired string. So why does this protocol perform oblivious transfer? Let's remember that we need to check two things. First, we want the protocol is correct. That is, if both Alice and Bob are honest, then Bob actually gets the desired string SC. Let's go through the protocol and see what could possibly go wrong. Remember that there is no noise on the quantum channel, so Bob definitely learns the bits xi. The substring where Alice measured in the same basis as his choice bit. That's great, but note that it could of course happen that Alice never measures in that basis. That probability is not so large. It's 1 over 2 to the n. Exponentially small in n, but still non-zero. Okay, so let's say that Alice did measure some bits in the basis C. We seem to be in good shape then. What she effectively does in this protocol is to produce two keys, one of which Bob can now compute. Bob gets the right key, KC, by the same argument as in QKD. He can apply the extractor to the input xi, he knows all of these bits, and the seed yc, he also knows. Then he can decrypt the one-time pad to get a C. Or can he? Maybe the string xi is also extremely short, like only a handful of bits, while the key that we need is very large as L, where L is the length of Alice's inputs S0 and S1. So to establish correctness, we are concerned with the string xi being of sufficient length. To check this, let's revisit how the strings are actually generated. If these are the bits that Alice has in the standard basis and these are the ones that she used the Hadamard basis, we see that the length depends on how often Alice measured in the standard and how often she measures in the Hadamard basis. The essential idea here is that since Alice chooses each element of the basis with probability half, the probability that the length of the strings, meaning the number of times, say, that she measures in the standard basis, is roughly n over 2. The probability that the length differs significantly from n over 2 is very small, vanishing as n grows large, in fact. This follows from the law of large numbers, in a more precise form given by Hoeffding's inequality. In a separate video, we will see that the probability that the strings do not have sufficient length, and we call this the probability that they're too small, can be made smaller than any desired epsilon by just choosing n large enough. We thus get that the protocol is epsilon correct for sufficiently large n. If the strings are not large enough, Alice will just pad them with random data. Bob will not know these bits, protocol will fail, not be correct, but that will happen only with very tiny probability. So how about security? Let's first consider security against a cheating Alice. I've removed here all actions of Alice from the protocol, since these actions can now be arbitrary. So what can Alice do? Of course, Alice could send Bob all kinds of funny qubits to measure. She can also send him a completely meaningless string that he will interpret as a basis string. But nowhere in the protocol is there any information going from Alice to Bob. And hence, it's easy to see that Alice cannot get the choice bit C. So why is the protocol secure against cheating Bob? This is quite a bit more complicated, and we will investigate this in a separate video.